Have you ever wondered exactly how a bridge collapses? Today, we're using a physics-based structural engine to test 6 different bridge designs. We'll analyze their load capacities, visualize the internal forces, and then push them until they reach their absolute breaking point. Let's get started. First up, the fundamental beam bridge. This is the simplest structural form, essentially a rigid deck resting on vertical piers. In our simulation, this design has a maximum rated capacity of just 400 tons. Let's start the inspection tour. As we apply the live load, pay attention to the force flow. The weight of the traffic pushes straight down, creating compression in the top of the deck and tension in the bottom. Traffic starts moving, force flow particles appear. You can see the load transferring vertically into the piers. But watch what happens as we exceed that 400-ton limit. Bridge starts shaking. The vibration increases, and there it is. The span suffers from excessive bending moment. The material yields in the center, leading to a snap-through failure. Simple but limited in strength. Next, we graduate to the through arch. By using a parabolic curve, we can span longer distances. Notice the significant jump in strength. This structure is rated for 1,200 tons, triple the capacity of the beam. Initiating the tour, the magic of the arch is compression. Those red ribs aren't just for show. They take the weight of the deck and channel it along the curve, pushing outward against the abutments. Force flow visualization. It's incredibly efficient for stone or concrete, but even arches have limits. Failure sequence begins. Watch the crown of the arch as the overload hits. As the abutments fail to contain the outward thrust, the arch loses its shape. We get a crown drop failure. The integrity reaches 0%, and the structure flattens and collapses. Now, the king of long spans, the suspension bridge. This uses steel cables in tension to hold the deck. This is our strongest contender today, with a massive capacity limit of 5,000 tons. During the inspection phase, look at the main cables. They follow a catenary curve, transferring all that weight to the tall towers and the anchorages. It's flexible, which is usually a good thing. Wind load increases. However, that flexibility is also its weakness against dynamic forces. We aren't just testing weight here, we're testing resonance. Bridge starts twisting. Look at the deck twisting. This is aerodynamic flutter, similar to the famous Tacoma Narrows disaster. The torsional stress snaps the suspender cables, and the deck tears itself apart. Here we have the modern favorite, the cable-stayed bridge. Unlike the suspension bridge, these cables run directly from the tower to the deck in a fan pattern. It's rigid and efficient, rated here for 3,500 tons. Let's run the analysis. Notice there is no main cable draping across the top. Every cable you see is under high tension, pulling the deck up towards that central A-frame pylon. Force flow is toggled. It's a redundant system, meaning it can survive minor damage, but let's push it to critical failure. Failure triggers. As the load exceeds 3,500 tons, the cable anchors begin to yield. Once the first cable snaps, it creates a zipper effect. The unbalanced load twists the deck, causing a progressive, catastrophic collapse. Going back to industrial roots, this is the Warren truss. It relies on triangles, the strongest geometric shape, to distribute force. It's incredibly rigid for its weight, with a capacity of 900 tons. This tour highlights the interplay between tension and compression. The top chord is being crushed, compression, while the bottom chord is being pulled apart, tension. Heat map stress view active. Watch the diagonal members in the stress view. As we overload the bridge, we're looking for buckling, structure shakes. There. A critical compression member on the top chord buckles under the stress. Because a truss relies on every member doing its job, the loss of one section causes the entire skeleton to crumple instantly. Finally, the cantilever bridge. This is a balancing act. It uses rigid arms extending from piers, often supporting a suspended span in the middle. It's a heavy-duty beast rated for 1,800 tons. In the inspection, notice how massive the structure is near the piers. That's where the bending moment is highest. The weight of the outer arms is actually balanced by the weight of the shore arms. Failure begins. But what happens when the center span is overloaded? Central span drops. The tension in the top cord snaps. Without that counterbalance, the arms can no longer hold the center span. It shears off and plummets into the river below. And that is how 6 different engineering masterpieces meet their end. Which failure mode was the most dramatic? Let me know in the comments. Thanks for watching and stay safe. Signing off, the Simulation Psycho.